All right, thank you for that introduction. Very kind. You might wonder what I do in my free time, right? Okay, so what I want to do today is talk about basically everything in the universe, give a quick summary from the beginning of what we can observe to how life and how much intelligent life we might have in the universe. So this is a lot of stuff, and I'll try to do it in a way which is connected, that is telling a story about how our universe evolved, that is how it changed from the very beginning until today, and how everything that we can see in the universe, at least in a very kind of grand way, we can sort of explain now through astronomy and physics and biology, etc. So the first thing that we can currently see in the universe, if we look with our telescopes, with our devices, with our instruments, is this. This is the cosmic background radiation, and this shows us how the distribution of matter was basically 300,000 years after the Big Bang. So when you see these fluctuations, you see the red and the blue and the green, this is telling you different temperatures of matter very early in the history of the universe. And that is a signal of the distribution of matter in the universe. Okay, so already we know, even back then, this is before any galaxies, this is before basically anything except mostly hydrogen gas, some helium, and maybe trace elements of lithium, and maybe a few others, but that's about it. But there's no real structures yet in the universe at this time. But you still see that there's overdensities in the universe. Okay, and this was long sought for many years. This was one of the great discoveries of the 20th century astronomy, was the discovery of this. And these fluctuations are only on the order of about 10 to the minus 5, or about 1 in 10,000. So these things took a long time to find. They were only discovered in 1992 by the COBE satellite, but now we can discover them routinely. And the thing about this is that we can use these fluctuations to determine the overall properties of the universe. And this is still the traditional way of measuring cosmology, that is the overall features of the universe to a high degree of accuracy and precision. Better than we can do it any other way. So if you want to understand cosmology, that is things like when did the universe begin, how fast is it expanding, things like that, how much matter is in the universe, how much dark energy, dark matter, the best way to do it is still to study this right here. And you may go, well, that's a nice, pretty picture of the early universe, but what does it actually tell us? Well, what it tells us is that you can look at, and this is something done with a computer, you can look at these fluctuations, how many there are, how far apart they are, how bright they are, and by studying this, you can determine the cosmology of the universe itself. And there's a whole science of that, and as I said in the beginning of my talk, I'm not going to go into great detail, but just to know that this is how we start off with our journey through the universe, is to understand the basic scaffolding and structure. And a way to do that is through this picture here. And when we do that, we can learn a lot about the universe. I won't go through all these numbers, but these are just the features of the universe that you can learn by doing an analysis of that picture I just showed you. And people have spent their whole careers doing that. It's not something that I've done, but it's something that many famous people have spent decades on trying to learn how to figure out cosmology from just that picture alone. Okay? And it's very important work. And this is the things that we have learned. And some of the more important things is the age of the universe is about 13.7 billion years old. Atoms, dark matter, dark energy make up about these fractions here, where dark energy is the most common. And atoms, what an astronomer might call baryons, okay, which is stuff that you make planets and stars and galaxies out of, that is only 4.4% of the universe. All the rest of the universe is of a substance that we do not understand, either dark matter or dark energy. Okay? And each one of those could be their own talk. But just to say that we don't know what they are, but they are an important component of the universe's history. Okay, so that's puts things in the context in terms of the universe. So we live in the universe. Everything that we see, everything that's happened has happened within the context of this. Okay? And if you could change that, and some people think that there are universes where these are different, but again, that's a whole other talk in itself, that you would get a different universe than we have today. The history of the universe would have been different. The final outcome of the universe that we can see today would be different if you change these things just by a small amount. That is the amount of dark matter, dark energy, the amount of baryons, the amount of atoms, you would get a different universe. Okay, so that's the big picture. Now, if we go back to the beginning, so to speak, astronomy really began by looking at this, looking at the Milky Way, at least one of the ways astronomy began. People have known about this for thousands of years, of course. Our ancestors looked at the sky, and it was much darker back then, of course, and they saw, maybe not in Britain, but in other places around the world, because of the clouds. It's a joke. They saw this big band of light called the Milky Way. Many different names of it throughout the world. Very important part of many people's cosmologies and religions throughout the world. And of course, today we know, since Galileo, that this is resolved into stars, and that it makes up the galaxy that we live in. And today we know we can make a model of our galaxy, the Milky Way, and we know that we're not in the center, although we did think that up until about 100 years ago. Believe it or not, we used to think that we lived here. We didn't know it was a spiral galaxy back then, but we thought it was the entire universe, by the way. So we've learned a lot in 100 years. But now we know the sun is 2/3 out from the center. So we're sort of in a nondescript location within a typical type of spiral galaxy. And spiral galaxies, this is another one that may look something like our Milky Way, if you could observe the Milky Way from far away. Spiral galaxies make up most of the galaxies in the nearby universe, at least bright galaxies. So bright galaxies are the ones that if you have a telescope, just a regular telescope, and you took it outside, or if you were even at an observatory, you just looked at the brightest galaxies, most of them, 70% or so, would look something like this, would have a spiral pattern. So these are the most common type of nearby bright galaxy in the universe. The other type of galaxy are the elliptical galaxies. Okay? And these are more spherical or elliptical in shape, hence the name, and they make up the remainder, for the most part, of the bright galaxies in the universe. Maybe 1/4 or so of galaxies look like this. And this difference between galaxy types in the nearby universe is actually really interesting. It's not an accident that galaxies are 75% or so spiral and then 25% elliptical. This number, this balance between these two, doesn't have to be that way. It could have been all spirals, it could have been majority ellipticals. And I'll come back to this a little bit. But the dependence on how many of these you have versus the spiral galaxies depends a lot on the cosmology, on how the universe is built up. And the reason is because these galaxies have an origin which is different from the spiral galaxies. And the way that we think about this, and this could change, the way we think about this is that spiral galaxies are formed from the accretion of gas. There's gas throughout the whole universe, and that gas falls into galaxies and it forms stars, and that star formation that you see becomes a disk, like a spiral pattern. Now, when two galaxies merge together, they tend to form something like this, an elliptical galaxy. And you can see this in computer models that have been around for now 50 years. That if you smash two spirals together, it makes something that looks like this. The spiral structure disappears, and you get sort of a amorphous blob of light, which we classify as an elliptical galaxy. And this is another one. This is a famous elliptical galaxy, and this has a dust lane through it. And these are pretty plentiful throughout the universe. Okay, now this is another example of a spiral galaxy, but this is starting to look like what we call a lenticular galaxy. So this is a galaxy that has a morphology which is sort of in between a spiral and an elliptical galaxy. And these are also fairly common in very dense areas of the universe. And sometimes these are thought to be galaxies which have fallen into a cluster of galaxies. And the cluster of galaxies, because of its intergalactic medium, has removed all the gas in the galaxy. And when that happens, the disk becomes quiescent. That is, no longer forming stars, and it looks like this. It starts looking very smooth without any obvious star formation. Okay. All right. And this was done, and these are classified now on the Hubble sequence, which is the traditional way that we classify galaxies. So you have the ellipticals on one part of the sequence, and you have the spirals here, which make this tuning fork, and you have barred spirals as well. It's just normal spirals, which make the top part, and the bars are down here. And this correlates to some degree with the properties of the galaxies. So it's not just how they look, but also the properties. This is a spectrum, and if you see these deep lines going down, that's an absorption spectrum. That means that the stars are old. When you see that, you know that you're looking at older stars. Because if you see something like this, where the lines are going the other way, that's a sign of star formation. The star formation is essentially heating gas, and when gas is heated, it emits lines. Basically, that's how it works. Okay, it's the same as in a laboratory on Earth. If you have hot gas and you heat it, it makes line emission. Okay, and so this typically correlates with spirals, and elliptical galaxies typically have this absorption line spectrum. That's a signal that they're older stars. So we know that these galaxies are typically older, and these are younger galaxies here. But these do have an older component, and sometimes these have a young component. So it's not exactly one-to-one ratio between history and morphology. All right, and that's excuse me. This was invented by Edwin Hubble. I assume everyone's heard of Edwin Hubble here? Yeah. So Edwin Hubble, American astronomer, came up with the Hubble sequence and the Hubble constant about the expansion of the universe. As you can see, he was an avid smoker of pipes. Yeah, so Hubble was actually a Rhodes Scholar at Oxford. So he's American, very much American astronomer. And he was a Rhodes Scholar at Oxford for about 2 years, about 1910 to 1912. But he spoke with a English accent the rest of his life and annoyed his American colleagues to no end. Okay. So I just wanted to say a little bit about other types of galaxies. So the Hubble sequence really is good for the most easiest to find galaxies, in a sense. Okay, an important thing about astronomy and galaxies especially is that just because galaxies are easy to find, some of them are easy to find, it doesn't mean those are the most important galaxies. It doesn't mean that those are all of the galaxies. It doesn't mean that those are the ones that you should only study. It just means that those are the ones that are easy to find. Okay, so galaxies can be very faint and hard to find. And these are some examples of this. These are low surface brightness galaxies. People heard of these before? Okay, some of you have. So what this means is that within a given part of the sky the galaxy occupies, the amount of stars you have is very small. And so when you look at it, it looks very faint. Okay, you can see here, there's another example up here, very faint galaxy. And these were not discovered until the 1930s. So this is even after Hubble's work in the 1920s, where he discovered basically the expansion of the universe, also the Hubble sequence. So these things are relatively recent compared to other type of galaxies. But we know that actually, and this is an example of the same level of a high surface brightness galaxy. And these are most of the galaxies that we know about today. But these low surface brightness galaxies are very common, surprisingly, right? Now, if you go out with a telescope and you try to just observe blank areas of the sky, you won't see these things because they're really hard to find. You have to actually have very, very good telescopes. Some of the biggest telescopes around. But when you actually use those to try to find these things, you find that they're very common. That these are the more common galaxies in the universe by number, okay? Not necessarily by mass. Right? If you add up all the mass of galaxies, these are actually low mass galaxies for the most part. But by number, they definitely dominate the type of galaxies in the universe. They're more the ordinary galaxy than the big spirals and elliptical galaxies. Okay, another type of galaxy is shown here. This is M82. I'm sure many of you know and love Messier. Right? And what you see here is a composite of H alpha light, which is this red stuff, and then the galaxy itself is just like a visual filter. Okay, and you can see that perpendicular to the disk, you have this outflowing stuff. Okay, so what is that? So this is an important mode of galaxy formation. It's not seen very often in the nearby universe because galaxy formation has more or less finished today in many ways, compared to at least the early universe, and I'll come to that soon. But what you can see here is that this red stuff is actually outflowing gas coming out of this galaxy, and this is most likely due to the effects of star formation. So when you have star formation going on, you make young stars, you produce lots of very massive stars, and we call these O stars. And these O stars have lots of energy coming out of them, lots of winds. So all this stuff is blowing material away from the star, and that also can blow material that's in the galaxy out of the galaxy. This is known as feedback. This is something that astronomers talk about quite a lot. And this is an important mode in galaxy formation. Now, another nice example is a composite of optical light. Here's a galaxy, a massive elliptical galaxy. And this is a radio image. Okay. So at Manchester, we study lots of radio imaging, so I'm getting used to doing that. I'm an optical astronomer, near infrared mostly. But radio is very important because it lets you see stuff like this. So these jets here are enormous. Look how far away they are from the central galaxy. So this is the same size as the galaxy I showed before. Right? So these extend way out here. And this comes from a central massive black hole in the center of this galaxy, also known as an active galactic nuclei, which emits these energetic jets. And these energetic jets can do very similar things as that outflows of stars can do. It can remove gas from the galaxy. It can heat the gas from the galaxy. This is another way of producing what we call feedback. Okay? When you hear feedback in galaxies, all it means is stuff which is counteracting the effects of gravity. All right? Gravity is a very effective force which just wants to move everything to the center. Right? And so if you look at very early models of galaxy formation, people did this in the 1960s and 70s just by on paper. You would get galaxies forming very rapidly if you just looked at gravity, right? So gravity would just compress the galaxy, you'd form stars very rapidly, and then you would just have a galaxy just sort of passively, we call passively because there's no star formation, passively change or evolve through time. There would be no new stars in it, okay? But we know that that doesn't happen. We know that galaxy star formation occurs throughout the history of the universe. Hi. And we know that this star formation isn't happening all at once. Okay? And one reason for that is this feedback mechanism, where you have these jets coming out, and this is sort of telling the gas, oh no, you can't form stars. It's pushing it out. It's heating it up. You need gas to be cold to form stars. If you don't have cold gas, you won't form stars. Hot gas does not form stars. Okay? You need gas to be cold to form stars. And so if you can keep gas hot, you can prevent star formation from happening. But if you can't keep gas hot, then star formation will occur because it'll be cold gas, cold dense gas will form stars. Excuse me. I'll talk about that again in a little bit. Okay, so you also see things like this, which is a galaxy cluster. So these are mostly ellipticals for various reasons. We know that elliptical galaxies form in very dense regions of clusters. So if you have a dense area of galaxies, usually most of the galaxies are elliptical galaxies. And you can see also X-ray gas surrounding or in the occupation of all of these dense areas of galaxies. So the denser the area of galaxies you'll have, the hotter this X-ray gas will be. And this has to be taken from space. This is X-ray imaging, and X-rays have to be done in space. So this, I think, is a Chandra space telescope image. Hopefully some of you have heard of Chandra space telescope. Right? It's above the atmosphere. So X-rays is one of the wavelengths that you have to study above the atmosphere. Okay, so this image was taken. The purple here was taken above in space. Okay, and the reason you see this happening in dense regions like clusters is because you have such an intense gravitational field, gravitational potential due to all of these galaxies in one location, that it essentially gravitationally heats the gas within these clusters. And when you have hot gas, it emits light in the X-rays. So the hotter the gas is, the shorter the wavelength it emits. And so X-rays is very short wavelength, very high energy photons. And so if you have a very dense, hot structure, it'll emit in the X-rays. And so do black holes. Black holes also emit in the X-rays. So this is called high energy astrophysics. And another thing you can often see is gravitational lensing, which I'm sure many of you have seen before. This is a really nice example here. We have this long arc. This is actually one galaxy which is behind this cluster, which is being magnified and distorted by the cluster itself. And you see this quite often in very dense regions like clusters of galaxies. And by studying this, you can get some idea of the mass of the galaxies that are producing that lensing effect. You can make a model, and people again have spent their whole careers doing this, but it's not something that I work on. And you can also magnify these distant galaxies, and so this is known as sometimes called nature's magnifying glass, because it's sort of doing the job of a telescope, because this galaxy which is being lensed is not only being distorted, but it's also being magnified. And this magnification could be many factors, could be factors of 100 even. And so this is one way that people study some of the first galaxies in the universe, is by looking for them being lensed behind massive clusters in the relatively nearby universe, magnifying the background galaxies so that we can detect them. Okay, and this is bound to be a powerful technique in the future as well. Okay, so that's our exploration of galaxies. So let's go back a little bit more and say, what does the structure of the universe look like if we go to larger scale? So if this is on an even larger scale, you start seeing galaxies cluster together. And this is a very old image. This is almost a historical image of just doing this experiment. This is from the Lick Observatory in the 1950s. And of course, Lick is a historical observatory, but has been very active since the 1880s, and still is today. And this was one of the things they did in the 50s. They just took plates of the night sky. So this was before CCDs. So they took very long exposures of just blank fields in the sky, and they just counted the number of galaxies they had in each. So it's sort of what like William Herschel did in the late 18th century, and just counted the number of galaxies they had in the plates. Of course, this is much deeper than anything Herschel could have done. And this is what they see. You definitely see places where there's more structure than in other places. And you can already see from just looking at where galaxies are located in the sky that there is a what we call large-scale structure. That is, that galaxies are distributed not in a uniform way, but clumped together. And then you also have places where there's no galaxies at all. Sometimes those are called voids, right? So you can see these places here where you see no galaxies. Some of these boxes, you have to be careful. These are stars that have not been bright stars that you can't count galaxies around because they're too bright. But you can definitely see like these walls and other locations where you see less galaxies. And that was expanded in the 1980s. This is also a very historic diagram. This is from the Harvard Smithsonian survey of redshifts of galaxies. So it wasn't not until the 1980s that astronomers were able to measure many radial velocities, or what we call redshifts, for galaxies. And that's just how fast these galaxies are receding from us. And because of the Hubble law, which hopefully some of you are aware of, but the Hubble law basically says the further away a galaxy is, the faster it appears to be moving away from us. So effectively, you can use that as a way to find distances to galaxies. Because if you see a galaxy moving faster away from us than another galaxy, then on average, that galaxy will be further away. And so this is a map of the velocity here, which is distance in an expanding universe. And this is a slice through the sky, very narrow sort of slice through the sky. Okay. And so what they found when they did this with these very massive sort of bridges and huge structures throughout the universe, And this was actually very surprising. I was not around then. Well, I was alive, but I wasn't an astronomer. I was just a kid. But when this was done, it was very surprising to astronomers because they thought this should be much more uniform. The galaxies shouldn't be distributed like this. And to me, it's sort of surprising, but I sort of grew up on this idea that this was, I grew up, but when I learned astronomy, grew up on the idea that galaxies are clustered like this because of the cosmology, going back to the cosmic background radiation, that galaxies are clustered because of the nature of the universe. So because of the way that dark matter, the way that dark matter is thought to exist, and we think dark matter is cold, and you often can hear about cold dark matter, right? So you've heard of that before? So we think dark matter is cold, not hot. So hot dark matter would be, for example, if dark matter was made of like neutrinos, which would be a really cool dark matter particle because we know neutrinos are very abundant and they have a mass, but not enough to be the dark matter. So we think the dark matter particle is cold for various reasons. And when you have a cold particle, what that means is, it doesn't mean that if you touched it, it felt cold. It means that it's not moving very fast. Okay? So it's cold because it's just slow moving particle. Whatever it is. You still don't know what it is. And when you have slow moving particles, they tend to clump together more. And they clump together more, and then they grow as time goes on. Okay, that's the idea. Whereas with a hot dark matter, something moving fast, neutrinos move close to the speed of light. You have structure forming on very large scales first, and then it gets smaller and smaller as time goes on. There's an opposite of what we see. So we see this clustering happening because of the nature of the dark matter particle, because we think it's cold. All right, so how do we connect this cosmology to the formation of galaxies? How do we do that? That's what I want to talk about now. And the basic idea, and this goes back to this cold dark matter, is that you start off, because dark matter is cold, very low mass dark matter halos. And dark matter halo is essentially just sort of think of it as like the container in which galaxies are forming in. So you think of them as blobs of dark matter. We call them a halo. So it's not like a halo like an angel has or something. It's a halo. It's just a spherical or ellipsoidal blob of dark matter that galaxies form in the middle of. That's all that really we mean by that. And those, because of the nature of the dark matter, will start off small, and then because of the structure formation in the universe, they will grow with time by merging together. This is a theoretical idea. And we'll get bigger, bigger, bigger. And eventually you'll have galaxies form within those dark matter halos when the gas gets cold enough to form stars. And that happens when the expansion of the universe occurs for long enough such that the gas gets cold enough, it's no longer being heated by various things, and then it can form a galaxy, and then dark matter halos can merge together to form another galaxy. Excuse me. All right, so how do we study this? So this is actually getting into some of the stuff that I work on. So the way that we have studied this process actually directly, so I'm going to move on from a theoretical idea to actually observations, is with this telescope. Anyone know what this is? Okay, people are laughing. Good. And the Hubble allows us to really study the distant universe in a way that no other telescope has before. And the way it works is the Hubble Space Telescope at the center of the universe here. And you have here the Big Bang, and you have the radiation era. This is the cosmic background radiation. And then you have this epoch here called the Dark Ages that we can't observe. And then you have the first galaxies we can see. And you can look at that through things like the Hubble Ultra Deep Field, which I'll talk about, and the Hubble Deep Field, and then you have galaxies today. So because of Hubble's deep ability to go very deep and to have high precision photometry and to be able to see morphologies, it's been a very useful tool. This is the Hubble Deep Field. I'm sure many of you have seen this before. This was taken the end of 1995, and this was a revolutionary picture for how galaxies are forming and evolving. And in this picture here, which is about 1 arc minute on a side, so it's very small, you have about 2,000 galaxies in here. And then further deep fields by Hubble have gone even deeper than this, and have found even more galaxies, all the way back to when the universe was about 500 million years old. And so the cosmic background radiation is 300,000 years old, and we can see galaxies back to 500 million. So between 500 million and 300,000, that's still quite a lot of time. And that's the epoch called the Dark Ages that we still haven't explored yet. But a telescope called the James Webb Space Telescope, which I'm sure all of you have heard of, will actually be probing that, and has actually started doing it this week. And we'll get some of the data in July. So that's very exciting. All right. So what did Hubble see? So this is a nice diagram. It's a little bit old now, but if you look at today's universe, you have spirals and ellipticals. But when you go back in time, and the time at the top is the time since the Big Bang. If you go back just 2 billion years after the Big Bang, galaxies are more irregular, they're smaller, etc., and they get more kind of normal looking compared to galaxies today, at least, as time goes on. You start seeing spiral structure forming, etc. And you can see that in various ways. Here are just some more pretty pictures of this. Won't go into more detail, but here's the ultra deep field of the Hubble Space Telescope, and you can see that galaxies indeed, as you look further back, they also get bluer and smaller. So galaxies, as you go further back in time, are more irregular, more peculiar. They look strange, at least compared to galaxies today, and they have small sizes, and they're undergoing lots of star formation. This is one of the key things about this. And this is the star formation history of the universe here. This is the age of the universe, and the star formation history peaks here at a couple billion years after the Big Bang, and then declines till today, right? And this is sort of a key of what's going on. So humankind evolves at the very end. Life appears on Earth at this point here. The solar system forms here. So I'll come back to this at the very end, but the solar system is actually formed very late in the history of the universe. We have all this time behind us here where galaxy formation, most of it has happened already. So our star, the sun, formed very late in the history of the universe. Okay, so we see this happening observationally. We see galaxies are different. Observationally, we see it happening. Why is it happening? And one of the ideas is that it's merging. This is something that I've worked on a lot throughout my career, is showing that merging is an important part of the galaxy formation process. Here's the antennae, famous example of a nearby galaxy mergers. Here are some more. These are all Hubble images, and you can see this is various phases of the merging process. So we know that merging is occurring throughout the history of the universe, but we don't know necessarily its role in forming galaxies. Okay, because we want to know how do galaxies form, right? It's not just something we want to observationally see happen, which we can. We want to understand what's going on. Are these peculiar galaxies actually mergers? And the answer is that a large fraction of them are. Here's some pictures of actual images from the Hubble Ultra Deep Field. These are galaxies sort of in the nearby universe, second half of the universe's history. So from about 6 to 7 billion years ago until today, galaxies look sort of normal. But when you go in the past, in the first half of the universe's history, the first 6, 7 billion years, you find that galaxies look very strange. They look peculiar. This number here is called the asymmetry. This is a quantitative way of measuring the structure of these galaxies, something I've worked on a lot. The higher the number is, the more asymmetric the galaxy is. Okay, it's a way of quantifying what your eye sees, essentially. So like these galaxies here are really asymmetric. They have high numbers. If this was 0, it would be just completely symmetrical. So you can see the galaxies are getting more asymmetric as you go further in the past. And so you can derive what is the galaxy merger rate based on that. And this is the first plot I'm showing here, so bear with me a bit. This is the galaxy merger rate. This is how many mergers are occurring as a function of time. And this is the time since the Big Bang. This is today here. And this is the early universe. We have a gap here, but we can start seeing and measuring that property of galaxy mergers quite early. And it changes for galaxies of different masses. So there's medium mass, low mass, and then you might call bright galaxies, but probably better to say it's massive galaxies. And you can see that the merger rate declines. That's the important thing, is that it's high in the early universe here and declines as you go further on in the history of the universe. So today, the merger rate isn't very high, but it is high if you go back and look earlier in the history of the universe. Okay, and this also correlates with the type of galaxies you see. Is the same kind of plot. here. This is the fraction of galaxy types. So today, here, the peculiar irregulars are real low, close to 0, maybe 1-2%, but the spirals and elliptical galaxies dominate the numbers. And this is for very massive galaxies, which is why the spirals are lower, because the more massive galaxies are elliptical in today's universe. But when you go back in time, you see that the peculiars jump up and they dominate the population. Okay? And we'll be able to really study this in more detail with this telescope, which will soon be everybody's favorite telescope, if it isn't already. And this will really probe even further back in time to the very first galaxies, where we can actually study this all the way back to these very first galaxies that we still haven't even discovered yet. So we will discover those galaxies, and it'll tell us what's going on in those galaxies in terms of its mass, its star formation, and also its merger history. And here's an early image. I'm sure some of you have seen this. This was released, I think, in March or April. This is one of the images that Webb looked at, and you can already start seeing that there's galaxies. This is a very poor reproduction. You can't really see much here. But if you look at it on a screen, you can see tons of galaxies. But this is the only image we have so far. So I have friends who have seen real images from the Webb. And I was in America last week and the week before at a meeting, and they were telling me that one guy told me he works at the Space Telescope where the Webb is being run from, and he's seen some of these first deep images, and he told me he can already see 5 things that'll change our view of the universe just by looking at the pictures. But he couldn't tell me what, so so I have to wait. And the first images will be released on July 12th, so put it on your calendar. This is going to be an important day in the history of astronomy. Okay, just to finish with this, the most distant galaxy ever is shown here that we know of. This will change maybe within a few weeks, but right now this is the most distant galaxy we have, and this is what it looks like. Right, nothing very exciting, and this is what we call the spectrum of it. Okay, this is just the flux as a function of wavelength, and most of this stuff here is noise, but this is claimed to be an emission line, and then also the continuum of the galaxy, which is not really important, except to say that where this is located tells us, because it's in the infrared, that this is a super distant galaxy. We think this is at redshift 11, which is a super high redshift object. But anyway, we'll learn more about this very soon. Just wanted to say also one thing about the cosmology, and I wrote an article about this a long time ago. Oh, I'm not as young as I look, maybe. Maybe I don't look that young anymore. But in any case, if you have a universe with more dark energy than we think exists, the dark energy that we think exists, and no dark energy, the type of universe you get changes. Okay, this is a really interesting thing, is that the cosmology of the universe determines the galaxy formation, and then likewise determines things about star formation, about the type of planets we have, type of metals we have, these kind of things. And so you see here that if you have more dark energy, the universe is more spread out, it's more smooth. Okay, and that's because you have dark energy is a way of expanding space very rapidly. And so if you have more of it, things will be smoother, you'll have less massive galaxies, you'll have less metals, because you need, when I say metals, I'm talking as an astronomer, metals, anything heavier than helium. Okay? Believe it or not. You guys don't laugh, that's impressive. Most students laugh when I say that. But you must know that already. So anything heavier than helium has to be produced in stars, because it's not produced in the Big Bang. And if you don't have a lot of star formation, you won't have lots of metals, and then therefore you can't produce intelligent life, unless you could find a way to produce intelligent life out of helium and hydrogen, which would be really interesting to see, but unlikely, I would say. Okay, so how do we get to those aspects of the universe after galaxy formation? How do we get to eventually life? So I want to go through that in the last few minutes here. So a lot of star formation happens in these kind of things. I'm sure you've all seen this Hubble image. This is the pillars of creation. This is where you have lots of dense gas and dust, and inside of this you have many stars being formed. And the star formation happens within these cocoons here, so to speak, and that star formation then produces also planets, and then which produces life. And I'm definitely not an expert in star formation. It's another topic which many people have spent their careers doing. But this is another example of star formation in our own galaxy. Here you can see the H-alpha filter producing these images where you can see the areas where you have star formation happening. And often star formation, or almost always star formation, happens in dusty regions in the galaxy. You need dust to form stars, and you need gas to form stars. Okay, you need both. And you can see a lot of this happening in galaxies. This is, I think this is M31, yeah, M31, although it looks very elongated here, but this is M31, right? Anyone disagree? Yeah, okay. This is the optical, and this is in the infrared and X-rays. You see these rings in M31. So this infrared is an infrared which is emission produced by dust. Okay, it's a fascinating topic here, and unfortunately I don't have time to talk about it, but dust will emit light in the infrared. And you can trace that dust, and this is where the star formation is happening. Here's a nice picture of it, just in the infrared. You can see that the bulge goes away completely. Okay, so how do we form life from that, right? How do we form life? That's what I want to talk about a little bit. This is where things get controversial a bit. And so the classic way is the Drake equation, which everyone hates, including me. And Drake equation, I'm sure you all know about that. You have all these quantities here. A fraction of stars that have planets, fraction which form life, blah, 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 right? But the Drake equation so this is a way of approximating how many civilizations you have in a galaxy. But you don't know what any of these things are, right? We don't know what any of these numbers are, so it's useless to use this equation. So if we knew how many intelligent species there were in our galaxy, then you could figure out these things, because we actually do know some of them. We know the average rate of star formation. We know that now. Fraction of stars that have planetary systems is about 15%. So we know that one. Number of planets around these stars with a ecoshell, meaning which can form life in like a habitable zone. We know that to some extent as well. But this one, the fraction of those planets where life develops, no idea. Fraction of living species develop intelligence, no idea. Fraction of intelligence, blah, blah, blah. We don't know what those are. Lifetime of civilizations, we don't know that either. So the Drake equation we can't ever solve the Drake equation until we actually know how many civilizations there are in our galaxy. Until we know that, we can't solve it. So an approach that we took with a student of mine, Tom Westby, is that we answered this question by looking at what we call the astrobiological Copernican method. And essentially this idea is that you say, okay, we don't know how life develops in the universe, but let's assume as a basic level of answering this question that life develops the same way it did on Earth. Okay? That you need exactly the same type of conditions, more or less, to form life. That it just doesn't form an arbitrary way, but you need a star which is at least 5 billion years old, like our sun, and you need, and it takes about that long to form life. So you can't have stars younger than 5 billion years, because some stars don't live 5 billion years. Some stars die much younger than that. So you need stars which last about 5 billion years, and then you can find out what fraction of stars have planets. We know that now from the Kepler mission. We know it's about 15%, and that's been shown to be the case for all kinds of stars, like our sun especially. It's about 15%. And if you know these things, and you know how many stars have a high metallicity content, that is, how many stars have high amounts of metals, like the sun does. The sun is a very metal-rich star. Then you can also figure all these things together. You can say, well, how many stars like the sun exist throughout the galaxy? And then if you make some estimate about how long the lifetime of a civilization will last, then you can figure out how many, or what is the minimum number of civilizations you would have in the galaxy, which would mimic the way that life formed on Earth itself. And so, as I talked about already, you need star formation to produce metals. So I've already gone through that. This is another example of where this is happening in the universe, and this is the history of the star formation again. And so we formed the solar system here, very late in the history of the universe. So you had all this time before, you have all these stars forming, and our galaxy star formation history is very similar to the universe's, that it mimics the way the universe is forming stars. The same kind of shape. You have this rapid increase early in the first couple billion years. It peaks and then it declines as you go to later times. So you know how old the stars are in our galaxy. We know that now. And you can use that information to answer the question exactly how many stars in our galaxy today are at least 5 billion years old. Okay. If you're younger than 5 billion, then you're not going to have intelligent life, according to the astrobiological Copernican principle. Because you need to have a life forming in the same way it does on Earth, which took about 5 billion years. Okay. The thing is, though, actually most stars in our galaxy are older than 5 billion years because of this shape here. Most stuff formed before us. Right? The sun formed very late. So most stars are older than 5 billion years because they formed around here. Okay. So that's not actually a very big constraint. But you also need to form planets. And this is a very fascinating topic in itself. Again, I don't know very much about this at all, to be honest. But you need heavy metals to form planets. And you can see planets forming. This is a Hubble Space Telescope image of Beta Pictoris. This is a famous star. And this star is famous because it was observed with some of the earliest infrared space telescopes in the 1980s. These are telescopes in space. And what these telescopes found was that Beta Pictoris, had an excess of infrared light. Everybody was like, well, why does this star have an excess of infrared light? And later on, they discovered it has a debris disk around it. And this is a forming solar system around the star. This kind of big black circle is just where the star is being removed from the image, right? So it's being occulted by a device, sometimes called a chronograph, and therefore it lets you see the outer parts around the star. All right, so this is 100 AU. So this is really small on a scale for looking at stars, at least with Hubble. But you can see that there's this debris disk, and this is causing this excess infrared emission that was seen with the infrared space telescope back in 1983, I think. And so we also have discovered lots of planets, of course. This is the number of planets found per year. Already 2022, we have already exceeded what we have in 2021. And this is only going to go up and up and up with time. This is a very impressive diagram. And Fraser talked a lot about this stuff as well, so I won't go into it too much. But just to say that what's very important as well to have stuff like us, intelligent life on a planet, is you have to be in the habitable zone, okay, where things are not too hot near the star and not too cold out here, okay? So you need stuff in the middle where you can form water in a liquid form, and that facilitates life when you have water. Okay, I think I'll skip that part. And then when did life actually develop on Earth? We have first life happening for about 4 billion years ago. We have human life about 300,000 years ago. Very smug caveman. And then we have communicating intelligent life, which has happened the last 100, 150 years since we've developed ways where something could detect our existence that we're intelligent, because we're emitting electromagnetic radiation, either lights, or now we have, of course, so many things, but various forms of electromagnetic radiation is going into space, and the invention of the light bulb was perhaps the first example of that. But of course, there's radio, television, satellites, et cetera, that go off into space. Now, the question is, how long will we last? So we've been a technological civilization that's emitting electromagnetic radiation for about 100, 200 years. So that's the maximum of how long that we know of any species of intelligent life has been emitting light that could be in principle detected. But how long will it actually last is a good question. We have many different ways of destroying the Earth. I'm not here to go into those and to say that we're all going to die soon, but you get the idea, right? So we could survive a long time, but we also may not, right? And so the most important part of this equation for understanding life and how much there is in the galaxy and the universe is how long it lasts. Right? So you have many stars which are very old and could have had civilizations that have existed billions of years ago, right? Because of that star formation peak, most of the stuff that's formed in the universe formed billions of years ago. Most stars are billions of years old, older than our own star, the sun. So you could have easily had life exist billions of years ago which, because it didn't last very long, even if it lasted 1 billion years, it would have already been dead when our own sun formed. So we're really latecomers to the universe, and so it's not clear how many civilizations may have existed in the past or exist today because of this lifespan problem. But if you just use the limit of what we know about humans, that we've been around 100 years, then if you just put all that together and say, okay, a minimum time of a civilization is about 100 years or so, as long as we've been around, then there should be still at least 36 civilizations in our galaxy, which is not very many. So if you just do the basic math, look at the astrophysics, and you use this number of 100 as a minimum of how long a civilization lasts, this is based on the fact that we've been around 100 years, then you get 36. And the closest one would be 18,000 light years away. So this is very far away. And they, of course, would not detect us because we've been emitting light only for 150 years. So it would take a very long time for any of that to ever reach the nearest one to us. But hopefully we'll live a lot longer than 100 years, and this number would go up correspondingly depending on how large that is. Okay, I'll finish there. Thanks for your attention, and thank you very much.
Thank you very much, Christopher. I think that explains absolutely everything.
Good, good.